In the name of Almighty God, I am Master Hassan Koshi, and today I want to talk about Fresnel equations or wave optics. A plane electromagnetic wave propagating through free space is incident at an angle upon an infinite dielectric medium. This model computes the reflection and transmission coefficients and compares the result to the Fresnel equations. The Fresnel equations are a set of equations in wave optics that describe how an electromagnetic wave like light behaves when it encounters an interface between two different media. They determine the amplitude of the reflected and transmitted waves based on the angle of incidence, the refractive indices of the two media, and the wave's polarization T or Tm. These equations are derived from the continuity of electric and magnetic fields at the boundary and are crucial for calculating energy distribution between reflected and refracted parts of a wave. What are the key concepts? The first one is interface, the boundary between two media with different optical properties such as air and gases. The next one is refractive indices, N1 and N2, properties of the media that describe how fast light travels through them. The next one is angle of incidence or theta I, the angle at which the incident wave strikes the interface. The next concept is angle of refraction or theta t, the angle at which the transmitted wave travels after passing through the interface, related by Fresnel law or N1 sinusite theta I is equal to N2 sinusite theta 2. The next concept is polarization, the direction of the wave's electric field vibration. The next one is transverse electric or TE. Electric field is perpendicular to the plane of incidence, also called S polarization. The next concept is transverse magnetic or TM. Magnetic field is perpendicular to the plane of incidence, also called P polarization. And what the equations do. The first one is quantify reflection and transmission. They provide reflection and transmission coefficients, which are the ratios of reflected and transmitted wave amplitudes to the incident wave amplitude. The next one is explain polarization effects. They are different for T and TM polarization, explaining how different components of light are reflected or transmitted. The next one is predict energy distribution. By squaring the amplitude coefficients, you get reflectance and transmittance, showing how much light energy is reflected and transmitted respectively. The next one is introduce Brewster angle. At a specific angle of incidence, Brewster's angle, there is no reflection for TM polarization light, a phenomenon used in various optical applications. The next one is total internal reflection. When light travels from a denser to a less dense medium, the Fresnel equations can predict conditions for total internal reflection at angles of incidence greater than a critical angle. The Fresnel equations or Fresnel coefficients describe the reflection and transmission of light or electromagnetic radiation in general when incident on an interface between different optical medium. They were deduced by French engineer and physicist Augustin Jean Fresnel, who was the first to understand that light is transverse wave, when no one realized that the waves were electric and magnetic fields. For the first time, polarization could be understood quantitatively, as Fresnel equations correctly predicted the differing behavior of waves of the S and P polarization incident upon a material interface. When light strikes the interface between a medium with refractive index N1 and a second medium with refractive index N2, both reflection and refraction of the light may occur. The Fresnel equations give the ratio of the reflected wave's electric field to the incident wave's electric field and the ratio of transmitted wave's electric field to the incident wave's electric field for each of two components of polarization. The magnetic fields can also be related using similar coefficients. These ratios are generally complex, describing not only the relative amplitudes but also the phase shifts at the interface. The equations assume the interface between the media is flat and that the media are homogeneous and isotropic. The incident light is assumed to be a plane wave, which is sufficient to solve any problem since any incident light field can be decomposed into plane waves and polarization. S and P polarizations. There are two sets of Fresnel coefficients for two different linear polarization components of the incident wave. Since any polarization state can be resolved into a combination of two orthogonal linear polarization, this is sufficient for any problem. Likewise, unpolarized or randomly polarized light has an equal amount of power in each of two linear polarizations. The S polarization refers to polarization of wave's electric field normal to the plane of incidence, the Z direction in the derivation in the picture that you can see. Then the magnetic field is in the plane of incidence. The p polarization refers to the polarization of the electric field in the plane of incidence. Then the magnetic field is normal to the plane of incidence. The name S and P for the polarization components refer to the German senkrecht or means perpendicular or normal and parallel to the plane of incidence. Although the reflection and transmission are dependent on polarization at normal incidence theta is equal to 0, there is no distinction between them, so all polarization states are governed by a single set of Fresnel coefficients and another special case is mentioned below in which that is true. 200 years ago, Augustin Jean Fresnel published the foundations for modern polarization optics. The goal is simple: compute how much light reflects from materials such as water or metal. In present times, the Fresnel equations are understood as a consequence of basic laws of physics. Energy cannot be created nor destroyed. Light slows down in a material and electric fields are continuous across a boundary or of two materials. Description of light. In the simplest terms, light can be represented by a traveling wave. There are two important terms used to characterize the light wave. The wavelength of light describes the distance between the peaks in the wave. The second parameter is the frequency of light. This describes the number of times per second that a single point can make a round trip oscillation from top to bottom and back to top. Frequency commonly appears in optic because the energy of light is proportional to frequency. This is important because a fundamental law in physics states that energy must always be conserved. This means that as long as the light wave exists, the rate at which a point oscillates up and down can never change. Material properties. Now, what happens when the light wave travels through a material? The simple answer is the wave slows down. Different materials slow down light by different amount. This is characterized by a parameter called the index of refraction and denoted by the letter n. The value n is equal to 1 represents the perfect vacuum. Water is near n is equal 1.3 and diamond is approximately n is equal to 2.4. The speed at which the peaks of the wave move from left to right slows down when n is increased. This is the main effect of the index of refraction for the material. Higher index of refraction means a slower speed. Secondly, the spacing between peaks also changes. As discussed earlier, the frequency of oscillation can never change. For every value of n, or index for refraction in the material, each point always oscillates at a quarter cycle per second. Having a slower speed with the same frequency means the wavelength must decrease. And what is about law of refraction? The consequence of light slowing down in a material is the direction of travel must change when light transitions from one material to another. This behavior is known as the law of refraction and is the basic of everything from camera lens design to the angle a rainbow makes in the sky. It's worth noting the law of refraction is commonly referred to a Fresnel law for work by Wilbur Snellius approximately 400 years ago. However, its actual use has been traced more than 6,000 years earlier to work by Abu Said al-Ala ibn Sahl. The best way to understand the law of refraction is to consider a collection of light waves all traveling in the same direction. As light slows down upon entering a material with higher index of refraction, the direction of travel changes. Calculation of this new direction angle is the law of refraction and satisfies the following equation: n1 sin theta 1 is equal to n2 sinus theta 2. In this equation, theta 1 is the angle of incidence and theta 2 is the angle of propagation in the second material. Both angles are measured relative to the surface normal. The waves n1 and n2 are indices of refraction for the two materials.